Hello everybody, and welcome to example 4 on page 69. Let's take a minute to read this example together. So consider the ordered bases beta equals 1 plus x and 1 minus x, and beta prime equals 2 plus x and 1 minus 2x for P1 of R. They'd like us to find the matrix Q that changes beta prime coordinates into beta coordinates. Okay, so this is another example of the type of problem that we did in the last video. The only difference is our vector space has changed. Okay, so we're talking about polynomials here. All right, so if we kind of use the little shortcut that we talked about in the last example, what we need to do here really is to start with the vectors in beta prime and to write those as linear combinations of the vectors in beta. All right, so we'll start by writing down 2 plus x and 1 minus 2x. And our mission is to figure out how do we express those as linear combinations of the vectors in the other basis. Okay, so we'd like to know what times 1 plus x plus what times 1 minus x will give us the 2 plus x. Okay, and then similarly, how would we get the 1 minus 2x? Okay, well, here's the thing. I'm not capable of looking at that and just figuring out what should go in the blanks because neither of these bases are terribly nice. They're not the standard basis. Okay, maybe you can look at the blanks and fill them in by inspection, but that's a little bit of a tall order for me. And so what I'm going to do is just ask the question, what would we need to put in these two positions? So we'll give those names A and B, and what would we need to put in these two positions? Okay, we'll call that C and D. Okay, so what we're gonna do is to try to solve for those constants A, B, C, and D. Okay, and to help us do that, we could simplify. Looking at the first equation, we could regroup that into A plus B plus A minus BX, and then similarly down here, we can regroup that into C plus D plus C minus DX. All right, and so looking at the first equation, for this to be a true statement, we need 2 to be equal to A plus B, and we also need the 1 in front of the x. Okay, I'm going to sneak a 1 in there. We need that 1 to be equal to A minus B. Okay, what that gives us is a system of equations that looks like A plus B equals 2 and A minus B equals 1. Okay, and we can solve that system. Okay, we can maybe take the two equations and add them together to cancel out the b's. That's going to give us a 2a equals 3, which would give us a equals 3 halves. And now that we know what a is, we can figure out what b is. So kind of looking at the second equation here, or actually let's look at the first equation. It doesn't really matter. Okay, I'm going to try to be consistent with my notes here. From the first equation, b is equal to 2 minus a, which we now know is 2 minus 3 halves. That's going to give us 1 half. Okay, so we've just figured out what A and B are. And we can now go up and ask, what would C and D be? Okay, well there, we need, let's see, C plus D to equal 1, and we also need C minus D to equal -2. That gives us a new system of equations. So C plus D equals 1, C minus D equals -2. And we go through the same process, add the two equations together. So 2c equals -1, which means that c is -1/2. Okay, and then looking at the first equation, we're going to get d is equal to 1 minus c, which is 1 minus -1/2. That's going to give us 3 halves. Excuse me. Okay, so we know what A, B, C, and D are. Let's start with the A and the B. They're going to give us the first column of our change of coordinate matrix. So A is, let's see, 3 halves, and B is 1 half. So we're going to get 3 halves and 1 half. Okay, and then next we need C and D. Okay, and looking at our work, let's see, C is -1/2 and D is 3 halves. Those two numbers are going to form the second column of our matrix, -1/2 and 3 halves. Okay, and there it is. We have just calculated the change of coordinate matrix, changing beta prime coordinates to beta coordinates.